Hello and welcome back to Calculus 2, section 7.8, improper integrals. It is time to change your behavior. From this lecture on, which will include all future calculus and math courses, engineering courses, and everything else, if you see a definite integral, you have to consider this. Otherwise, you will make some terrible mistakes in life. As engineer, that might mean exploding devices and devices that you don't want to be exploding. For instance, batteries and things like that. You see, explosion is release of large amount of energy over a short period of time. And we are going to deal with unbounded integrals whose area under the curve could shoot to infinity. In application, that means energy shoots up to infinity. Or finite time is the explosion. So when you fail to recognize these things, you create a battery that looks great in every aspect and it explodes. And you have few companies that had those issues, whether the computers, the cell phones, and so on. So you have to be able to detect this. We are going to cover two different types of improper integral. Type 1, which is going to have infinities clearly visible in the limits. So type 1 technically screams, be careful. The evil one is type 2. Type 2 has your regular limits a and b. But what it has is a vertical asymptote within that interval or at one of the endpoints. So for type 2, there is a vertical asymptote in AB. And note that I have the square brackets, which means including A and B. So vertical asymptote could be A, could be B, or anywhere in between. Now those, most of the time, create infinite area under the curve. And if you miss that as the engineer, whatever you're making is not going to be good. So type 1 is extremely simple because you see that there is an issue. You take a function, say 1 over x. And you are interested or the area on the interval 1 to infinity. Well, you know how to set up that integral. Area is a definite integral from 1 to infinity. 1 over x dx. Now, you cannot plug in infinity. So what we do is we cheat. We replace the infinity with a finite value b and then we send that b to infinity in the limit. So now we can integrate, right? Ah, the software exploded.
I don't think they took account of improper integration.
Yeah, it has to go all the way to infinity. So what we are doing now is just a regular integral, and we are computing at b. And then we're going to do the limit later. So we have the limit, b goes to infinity, and we have our ln of x computed from 1 to b. Cool. That's the limit, b goes to infinity. And now you have your ln b minus ln 1. ln 1 is 0. So we're good there. Now what's ln of infinity? What's the ln of infinity? It's infinity. If you take a look at the end behavior, as x goes to infinity, the y goes always up to positive infinity. Right? So, it is probably something you expected, because the graph shows when you start at 1 and you go to infinity, you consider the area under the curve, which is all of this. We see that area is leaking forever to the right. So maybe you expected it to, what we say, diverge, which means go to infinity. We'll say like this. Diverges. I put D in a circle. Let me see. Now I want to consider very similar function, 1 over x squared, on the same interval 1 to infinity. And I want to ask you about the area. Use the same steps. Area is equal to the integral 1 to infinity of 1 over x squared dx. Substitute the limit in there, do the integration, and then do the limit at the end. All set with the problem? I don't know, I haven't done it yet, but it does converge, so could be.
And then I'd be at work at 3. And then my work is coming 3 to 2. And then I would go into service at 5. So, or I would go in early, like that, because like, there wasn't enough time in the day. So I did that for a week before I had to go to the show. Yeah, like, I know I never know. I made some money though for those 2 weeks though.
All right. So we start by limit. Since the upper limit needs to be changed, I will use b. And then I have x to the minus 2 dx. You have to copy this limit every single step all the way till you're done. This is going to be negative 1 over x to the over x, right? And the limits are 1 to b. So again, limit b goes to infinity. And we have negative b over, no, negative 1 over b. What's going on today? You all decided to come here and test there?
Professor. Die on you.
Nice. Keep going. Plus 1 over 1. And 1 over b is 1 over infinity, which is 0. So we have 0 plus 1 is equal to 1. And we have convergence. So we'll say area converges to 1. converge. You know what it means when it converge. Things converge, yes. Oh. Right. I will just talk. You will write down things. What do you mean? So the previous problem, the answer was 1. We put C in a circle. We say converges. And now the next problem, because we can. What happened? Yeah. Don't forget that you all have computers in front of you, and you can watch the stream on the computers in the desk. But I will reboot the projector, so eventually it will be up. You can also follow it on your phone, which is connected to Wi-Fi. You can have your laptops out and so on, so you can still see what I'm writing. The projector doesn't have to be up. But we'll wait for the projector to cool off, and we'll restart, and hopefully...
It's still 7.7.
I'll change it later. It's fine. Thank you, though. The next problem that we are going to look at is one of the homework exercises, and type 1 is done. There's really not that much about type 1. You use your eyes to see the infinity, and you replace it in a limit, solve the integral, and then just work out the limit. Hence my next example. Yes. I said we'll do one more example. Yeah. So this is problem 20 from textbook, and it's negative infinity to positive infinity, dx over x squared plus 2x plus 5. So dx over x squared plus 2x plus 5, and the limits are negative infinity to infinity. Now, here's the issue. You cannot put two limits, right, on the pile. So you cannot put a limit and then put A and B at the same time to go, right? So what happens is, I hope that worked. I'm just going to, let me just restart the projector. Intelligent stuff, I mean, what you can do. Now, please remember from your Calculus 1 that you are allowed to break the integral at any point in your domain. The theorem said that the integral a to b of f of x dx is equal to integral a to c of x dx plus c to b of f of x dx. So as long as this c is in between a and b, so you are allowed to pick any number between negative infinity and positive infinity. Any number. 0. So you are going to now work out the integral negative infinity to 0 dx over x squared plus 2x plus 5 plus 0 to infinity dx over x squared plus 2x plus 5. Now, good thing about these is that the integral is the same. You just have to worry about different limits once you are done with integration. So to set up this fully, you have limit. Now look, you have negative infinity. That's a lower limit. So we're going to use a in this case. If you're replacing the lower limit, you're using a. If you're replacing upper limit, you use b. So you have to set it up first. And once this is set up, you have the limit for the second one. Now use b because it's the upper limit. So we have 0 to b. X squared plus 2x plus 5. There we go. And now you need to integrate. How do we integrate? Can we factor it? To use partial fraction. It was suggested to use partial fraction decomposition. No. We cannot. Yeah, we cannot factor this one. And because we cannot factor, we cannot use partial fraction decomposition. Also, you have to see, now you are not experienced in this, so it's okay not to know at this point or not to be aware of it at this point. But if you were able to factor this, you would be in so much trouble with this integral. Because if this factors over 2 integers, you would have 2 vertical asymptotes. And that would create another 6 integrals on the pile. You don't want that. So you are lucky that this doesn't fit the partial fraction decomposition. But it does fit trig sub. Now how do we do trig sub on this? What do we have to do? Well, I first have to transform this in order to do the triangle. What was the... What one? I thought I heard it over here somewhere. What do I have to do? What do I have to use? No, Pythagorean, no. Is this in a form? Is this in a form? In a proper form for trig substitution? No. How do we transform it into the form for trig substitution? Complete the square. Yeah. Completing the square. So we have to unleash completing the square first. That will give us the form for trig sub. Then we do trig sub. Then we do limits later on. Oh yeah, each problem is a page. The homework is going to be awesome.
Did you do integration by parts or not?
How?
I was just curious. I was asking.
What, did you try it?
I started.
And?
I didn't finish it because you said you trigged that. Okay.
Oh. I said things and then you just... All right.
I'm like, oh, okay. Word for it.
Yeah, let it go, let it go.
Why wouldn't it work?
Try it. See, that's the part, that's the issue with this generation.
No.
Just want to know the answer right off the bat with zero work invested.
I don't even know how to.
I know, I can thank internet for that, sure. But, yeah, why integration by parts, here it goes on a stream, I don't want to tell you. Try it, and you will discover why. I'm a terrible person, and I'm proud of it. completing the square. We are going to group first two. We are extracting b, dividing it by 2, squaring. We get 1 squared, which is 1. And that's the magic number, which we add and subtract to complete the square. So we have +1, -1, and then we still have the +5. Now, I could have stolen a 1 off of the 5 and still have the 4 there, but that's okay. So when I group the first 3, square root of the first, sine of the second, square root of the third, everything squared, and we have +4. Look at that. Perfect. 2 perfect squares. So now, to do the trig sub over here, we have addition. So these are our legs. These are our legs. And this one over here would be the square root of x plus 1 squared plus 4. This triangle is terrible, because I'm standing up instead of sitting down. All right. If you recall, we are creating 2 trig functions towards the constant, right? So we have the red equation, which is a tangent. So tangent theta is x plus 1 over 2, from where x plus 1 is equal to 2 tangent theta, and x is equal to 2 tangent theta minus 1. Immediately dx is equal to 2 secant squared theta. That's immediately. We have x and we have dx. What happened with my d theta? There we go. Then we have the blue equation. The blue equation is going to be cosine theta. And the cosine theta is 2 over the, I'm just going to write it as a square root. I'm not going to write the content of the root every time. And then from there, square root alone is equal to 2 secant theta. Now, since we don't need a square root, we have to square both sides. And that will give us what we actually need. So the blue equation says that x plus 1 squared plus 4 is equal to 4 secant squared theta. Perfect. Now I'm just going to solve the integral, and then I'm going to go and plug, because I don't want to write the limit 15,000 times. So I'm just solving the integral now, which is dx over x squared plus 2x plus 5, which can be rewritten as the integral. And instead of dx, I have 2 secant squared theta d theta. And instead of the denominator is 4 secant squared theta, this part. We know that this and this is the same thing, right? You do completing the square and you just put it in a different form. So now, when we cancel everything, oh, look at that. How awesome is this? We have 1/2 integral d theta. That's 1/2 theta. We're not going to use plus c because we have to deal with the definite integrals later on, right? And they will use the limits, and the plus c is not needed. So 1/2 theta, and the theta can be inverse tangent up there. So 1/2 inverse tangent of x plus 1 over 2. This is the value of our integral that we are going to plug into our limits. So back to the problem. And if you think this is long, wait for chapter 8. I mean, wait for differential equations. we have limit a goes to negative infinity of 1/2 tangent inverse x plus 1 over 2 computed from a to 0 plus limit b goes to infinity of 1/2 tangent inverse of x plus 1 over 2, 0 to b. Limit a goes to negative infinity of 1/2 of tangent inverse of 1/2 minus 1/2 tangent inverse of a plus 1 over 2. All of that plus limit b goes to positive infinity. I mean, all of this is with the first limit. And now the second one is 1/2 tangent inverse of b plus 1 over 2 minus 1/2 tangent inverse of 1/2. I cannot apply limit to the first term because there are no a's in it. Therefore, that term is copied in front as is. I apply inverse to the second one. Now, I have negative infinity. So the whole thing here becomes negative infinity, because when you add 1 and divide by 2, you don't change it. It's still negative infinity. The negative sign in a tangent, because it's odd function, jumps outside and makes this plus 1/2 tangent inverse of infinity. We'll deal with that. Plus another 1/2 tangent inverse of infinity. And finally, minus 1/2 tangent inverse of 1/2. Now, if you don't remember the graph of tangent inverse, then you are not paying attention when I told you make sure you know it. Tangent inverse graph looks like this, and you see that as x goes to positive infinity, the y caps at what value? Very good. Pi over 2. So the first and the last cancel because they are exactly the same quantity with opposite signs. We call it additive inverses. And what you're left with is 1/2 of pi over 2 plus 1/2 of pi over 2, which altogether is pi over 2. If you take 1/2 of pi over 2 and add another 1/2 of pi over 2, you get 1 whole pi over 2. Or you just use the quarters. So this problem had two infinities on the upper and the lower limit. We broke that at 0 and dealt with two separate problems. I took a whole page, right? Yep. And we get to review partial fraction decomposition, because it wasn't that. Integration by parts, because it wasn't that. And then finally trig sub with whatever that it's called, now I can't remember. Completing the square. There we go. Let's open the gates of hell. Type 2. What happened? Yeah, we covered the easy one, type 1. Now we get to the tricky one. Now this one is, you know, calculation-wise, absolutely same thing. Same thing. It's not going to be longer. It's not going to be shorter. The evil part about this is that the problems look the same like a regular Calc 1 problem. And then you try it, and if you're not careful, you solve the problem and you get the wrong answer. Typical example of the wrong thing to do is to calculate 1 over x from -1 to 1. You see? Well, actually, no, you can't do that because of the 1 over x squared. 1 over x squared from -1 to 1. If you compute that, you're going to get the number at the end. But that number is garbage. Because 1 over x squared has a vertical asymptote at 0. Right? Which is where area leaks. And that area could converge or diverge. And if you don't use limits, you are going to get the problem wrong. So the issue is here that the problems that you are dealing with look perfectly normal. Like dx over x minus 2 from 2 to 4. See that? Wouldn't you agree that this is a basic U sub problem from Calc 1? And the answer is hell no. It's not. Because where's the vertical asymptote? At 2. And what do we have as one of our limits? 2. So that is the part where you must unleash your limit. You will make x approach 2. And you will replace that 2 with a. You will solve the integral with your ln and blah, blah. And then you will apply the limit as a goes to 2. And then it will converge or it will diverge. So these problems now are not computationally crazy. Sure, you can get trig sub, U sub, and all the other stuff. But the evil part is, are you going to recognize this? And that's what I said. And especially the ones that bury the asymptote inside. This problem is so easy to do, and I can just put 1 to 4. 1 to 4, right? Asymptote is buried inside. If you don't catch that, problem is wrong, right? Points off on a test. Big deal. If you miss that in application, you have infinite buildup of energy. Because energy is area under the curve. And what did we talk about? Right? So these you have to be very careful. If you, depending on what, depends on what kind of engineer you want to be and work on what level and what type of research and design and so on. But those are the things that you absolutely have to be careful about.
So does that mean from now on we should always be
yes. This is why I said today, this lecture changes your approach towards every single definite integral you're going to see across all math courses, all engineering courses, later on for your application. This lecture tonight changes your behavior. It's not let's integrate. The first thing you have to do is chase asymptotes. That's the first thing you have to do. ln, if you have ln inside, ln has the vertical asymptote at 0. Square root of x not defined left of 0. Right? Vertical asymptote every time denominator is equal to 0. You cannot have a tangent problem and integrate tangent from 0 to pi. Because there's asymptote at pi over 2. Whatever you get is going to be wrong. So now you have to consider this situation and realize that here in blood, which means that we have to unleash the limit. Limit a goes to 2 from the right So 2 plus, right? And then you have the rest of your limit, the integral, a to 4 dx over x minus 2 equal to the limit. A goes to 2 plus. You know that this is going to work out to be ln absolute x minus 2 because we did 5,000 of these, right? Did we? Yeah, you practiced the homework for partial fraction decomposition. If you haven't seen 30 of these little ln's like this, then you haven't done your homework. Computed from a to 4. You will plug in your, so limit a goes 2 plus. You will plug in your ln, and you have ln 4 minus ln of a minus 2. And this is where the fun begins. 2 minus 2 is 0. And you know what happens to ln graph as you approach 0 from the right. What happens? You are approaching 0, negative infinity happens. Very good. So the whole thing is ln 2 plus, right, minus and minus make plus, plus infinity. That will be divergence. What happened?
Would that be the correct answer to put down on test, or would you prefer, or would you accept just positive infinity? Because ln of 2 plus infinity would still be infinity.
Yeah, it's yeah, we could write infinity.
Either one would be acceptable.
Now we just want to write infinity, and then put the divergence right there.
Okay. Do you want us to put the divergence then?
You have to put divergence. This is your 2 points final answer. Okay. Divergence. That's the 2 points final answer when you say diverges. That means, well, I'm sorry? That's the answer. Because we are asking if it converges or diverges. Convergence means, let's say you get number 2 is the answer. Then if number 2 is the answer, you will say converges to 2, which means area is 2. If you have infinity, then you say diverges. So on this problem, if I box this, I say divergence, and that's the full credit. Previous example, when the projector cut out, right here, area converges to 1. That's your 2 points.
So the answer is infinity.
The answer is infinity, but we write divergence. Okay. So this is the answer that we are looking for. Blasphemy. Converges to pi over 2. Thank you. Well, I lost 2 points there. Good thing that I'm not taking the test. So, all right? Imagine that. Ready for the next one? Yeah, you're ready for the next one. You love this stuff. We can do another. Let's practice a little bit of the trig integration, since I know how much you love this stuff in 7.3. How do we integrate this? U sub, yes. Sine over cosine, U sub, and we're done. So, limit b goes to pi over 2, that's the problem point. Integral 0 to b, sine theta over cosine theta, d theta. And then we do u equal cosine theta du equals negative sine theta d theta. Limit, I know the value of this, so I'm not going to work out the details. It's going to be ln of secant theta plus tangent theta, right? No, it's just integral of secant theta. Yeah, and then when you take the negative inside, it becomes 1 over cosine, which is secant. You have to have tangent secant pairs. From 0 to pi over 2.
I'm sorry, I didn't understand. Why is it?
You have a negative in front, right? And you have a cosine inside. When it goes cosine to the negative 1, cosine to the negative 1 is 1 over cosine, which is secant. And that takes care of that. Oh. So now we use oh, this is not supposed to pi over 2, it's supposed to say b. There we go. So limit b goes to pi over 2 ln secant b minus ln secant of 0. Now, how much is secant of b? Secant of pi over 2. Well, that's a cosine. Cosine of pi over 2 is 0. So that's the one that explodes, right? And secant of 0 is 1, ln of 1, so minus 1 over here. No, minus 0. So the whole thing is infinity, and it diverges. If you are still not certain what happened, Secant you can write as 1 over cosine theta, and that leads to 1 over 0, because cosine of pi over 2 is 0. So 1 over 0 is infinity in the limit. All right, one more. 42. All of these problems are in your textbook. So you have integral 0 to ln 3 e to the x divided by e to the x minus 1 to 2/3 dx. Where is the problem? 0. 0 is the problem. Because it will create 1 minus 1 in denominator, which gives us 0 in denominator. So we start with the limit, and a goes to 0. And you can say from the right, if you want to, of the integral a to ln 3 of e to the x divided by e to the x minus 1 to the 2/3 dx. We use u sub, right? So e to the x minus 1 du is dx. It's not there for decoration. This dx replaces this dx. You have to have it, otherwise doom. Integral. I should be swapping these limits, but since I'll go back to, so I don't have to change this one as well. I'll go back to x. So just briefly, we have du over, so u to the negative 2/3 du and what do we get? You get plus 1, right? So u to the positive 1/3, so that's cube root of u divided by, no, times 3. I need the integral. So limit goes a to 0 plus, and now I have ln 3 to plug in. So that's 3 minus 1 is 2, so 3 cube root of 2. Minus 3 cube root of e to the a minus 1. Three cube root of 2 stays as is, and when I plug in 0 here, I get cube root of 0, which is 0. So it converges. You have to. So asymptote in this case was at 0. Yes. 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 We have time for one more. Yes or no? No? You're done? But this would be application problem with, you know, volume and rotation and stuff, no? Monday? Yeah, we have 9 minutes. Yes. Well, you have to lie when it benefits you. I mean, it's.
You seem very excited.
Of course, they're going to be very excited. It's cool stuff. Actually, we can do the word problem. There's one more that we could do. I promise you will love this one.
Have a nice weekend.
So are there any issues with limits or no? Yes? Where is the issue? At 0. Very good. ln has vertical asymptote at 0. Therefore, we have the limit a goes to 0, integral a to 1 x ln x dx. Great. We're able to set this up. Now what? Integration by parts. Very good. Very good. Now, what is u? What's dv? What should I do? U is ln x. Nice. And dv is x dx. So du is 1 over x dx. And v is x squared over 2. And the arrow helps us with the formula. Don't forget your limit. A goes to 0. And now what do we have? We have x squared over 2 ln x minus the integral, and this becomes 1/2 in front x dx, right? Are we good on this? From a to 1. So limit a goes to 0. The first part 1/2 x squared ln x minus 1/2 x squared over 2 from a to 1. Do we still have any issues? Well, we have to take this limit. And what you have there is 0 times infinity. Do we remember what we have to do for those? Yeah, exactly. L'Hopital's rule. Nice. So we have to do L'Hopital's rule here. We have 0 times infinity, and we use the trick that f is equal to 1 over f. Great. Limit a goes to 0 of 1/2 a squared ln a. We have to solve this limit. So we take this a. We don't have to worry about 1/2 at all, right? We can just solve the limit and see if it's finite. We can multiply whatever we get with 1/2 at the end. I can factor 1/2 actually in front of the limit and then not have this 1/2s around. Whatever. So we have this. What we do is we say that manipulation here is to leave ln a and then write as 1 over a squared. So now we have infinity over infinity, which means that we can use L'Hopital's rule, differentiate numerator and denominator separately. So limit a goes to 0. The derivative is 1 over a, and the derivative down there is what? -2 over a cubed. All together, this becomes a squared. So limit of a squared, I mean, there are other constants and things, but it will go to 0. So is 0. So now back to problem. We had to solve this L'Hopital rule. We're going to have a lot of these L'Hopital limits coming up in chapter 8. So get. I said that day one. You could have quit there. You sat in this class, and chapter 8 is coming up. Every problem is a limit problem. Mass of them are L'Hopital rule. So get cranking that stuff. So the first one is, okay, so what do I have? I have 1/2 limit a goes to 0 of 1 squared ln 1 minus a squared ln a minus 1 squared over 2 and plus a squared over 2. We know that both of these terms go to 0. We calculated this one. This one is clear that it goes to 0. We have 1/2 limit. No, limit is done. 1/2. Now ln 1 also goes to 0. So that term dies as well. And all I have is negative 1/2 over here. So negative 1/4. You got it? Negative 1/4. And there you have it. Improper integration. Have fun with the homework. See you all next week.